Chapter 7. Heather, right? You had the question? Was it chapter 7 or chapter 8? Chapter 7, number 28. Okay. Let's take a look. So, maybe. All right. This is talking about the mean incubation time for fertilized eggs at certain temperatures, 18 days. Suppose that incubation times are approximately normally distributed with a standard deviation of 1 day. Complete parts A through E. Draw a normal model. I'm guessing it's probably like part D that you have a question on maybe or something. Yeah, okay. Well, we can go through anyways. Choose the correct one, group graph A. So it's supposed to be centered at 18 with a standard deviation of 1. So this looks like it would have a standard deviation of 2. That doesn't work. That one looks okay to me. Let me just click the other ones to see. Nope, that's centered in the wrong place. That's centered in the right. Oh wait, no, this one's right because it has a standard deviation of 1. What was the other one I said was right? What was wrong with it? Oh, it's centered in the wrong place. Oh yeah. Okay, there you go. Good thing I didn't pick that right away. Okay, cool. Find and interpret the probability that a randomly selected egg hatches in less than 16 days. Okay, so let's see here. We're gonna go with. Man, this thing. Watch me. Now I'm gonna break the computer myself. Maybe. New, like, we should do one of those cool colors. Okay, so we're looking for the probability that it's less than 16. Is that what it said? With a mean of 18 and a standard deviation of 1. So we're going to go for, so it's a mean of 18. So here's 18, which is the center. 16 is down here. We're looking for something like that. Okay. Let's see. If I check this actually. So we're going to go, we need to get a z-score here. Correct? So the z-score for this particular observation is going to be 16, that's the observation, minus the mean 18 over the standard deviation, which is 1 day. Right? Because the idea here was that mu is 18, sigma is 1. So this is just going to be a standard, this z-score is going to be -2. Okay? So what I'm actually going to go do is I'm going to go to the z table and I'm going to go look up the probability of being less than -2. All right, z table. All right, and again, I'm irresponsible, so I don't have a paper copy of this. So we get to wait again. Whoa. Ah, no. What am I doing for e-text? Did I just get rid of my homework on accident? Oh, no, it's still there. Cool. You know what really bothers me about that? Why do they have 2 status bars? One fills up and then it gives you another status bar to tell you to wait longer. That's annoying. Okay, here we go. So -2.0, so the area below it, -2.00, so it looks like 0.0228. 0.0228. So that's going to be the solution, I think, for this part. Let's try it. Did it yell at me now? Let's go. Chill. What'd I do? Yeah? Okay. Wait, it's going to redo this all, isn't it? No! Ah, we're about to find out. It's like watching your grandma use the computer. There we go. All right. So here we go. So then I'm going to go, it looks like it left everything the same. So it's 0.0228, correct? Is what we got? Okay. The next part says, interpret this probability. So it's saying basically, what does that actually mean? It says that if 100 fertilized, so one possibility is, if 100 fertilized eggs are randomly selected, blank of them would be expected to hatch in less than 16 days. In every group of 100 fertilized eggs, blank eggs will hatch in less than 16 days. The average proportion of the way to hatching of the, I think it means days, to hatching of all eggs fertilized in the past 16 days is blank. One of those is reasonable, 2 of those are not. Why? Which one can we rule out for sure? B. Why? I agree, but why? Yeah.
Guaranteed.
That's right. So that's the problem with B. B is like saying it's definitely going to happen, but this is a probability statement, right? That just because of probability, if something is a certain amount, doesn't mean it's necessarily going to happen that often. What's the other one that's probably not? C doesn't seem normally, first of all, because it's not a coherent sentence. But I think that's because there's a typo in it. But even if it said what it was supposed to say, I don't think it makes any sense. It would say the average proportion of the days to hatching of all eggs fertilized in the past 16 days. See, the past 16 days has nothing to do with this at all. It's talking about the... Anyways. Well, see, and even then it's saying... This is like saying the average proportion is saying it's like something that was actually realized, which probability does not say. It's something that you expect. So that's why I think this one's okay. So if 100 fertilized eggs were randomly selected, then blank of them would have been expected round to the nearest integer. So basically we're saying that like 2% of them are going to hatch that fast. And so it would be like 2. It would be 2 eggs, I think is the answer. Okay. That was both part B? Jeez. Okay. Find and interpret the probability over 20 days. Same idea here. Now we're just going to go get, so the probability of over 20 days. Well, our z-score is going to be 20 minus 18 over 1. Well, that z-score is just a positive 2. So notice that it's going to be above 2 is going to be the same as below negative 2. So if this was 0.0228, this would also be 0.0228. So I think the answer here is going to be the same. So we'll go back, maybe. All right, so I'm thinking 0.0228. All right, likes that answer. Interpret that. It's going to be the same thing. And if 100 fertilized eggs were randomly selected, you would expect 2 of them to take more than 20 days to hatch. So same answer there. All right, how about between 17 and 18 days? So now we're going to do the same thing, but our z-scores will change a little bit. So probability, we'll go probability between 17 and 18. Okay. You know, so it's centered at 18. Here's 17, and I want to know this. Yeah. So the z-scores for both of them. So for 18, that's the mean. So its z-score is just going to be 0. The other z-score is 17. That z-score is going to be a negative 1. Okay. So we need to go look up, well, we really don't need to look up both of these. I know what the probability of being less than 18 is, right? It should be just 50% because it's halfway. Z-score is 0. It's just going to be 50%. We could go look up, we do want to probably go look up negative 1 in the table. So if we do that, yo, dude, chill. Don't be so angry at me. Oh my gosh, what is going on here? There we go. Look up negative 1. Negative 1.0 is 0.1587. So that would be, this one's going to be 0.1587. So how do I get the probability in between? You just do what? Yeah, you take the big probability minus the small one. So that's 50% minus 0.1587. And so that's going to be, what, 0.4413 maybe or something? Or is it 2.3? Oh, I just made stuff up, apparently. Okay, yeah, 3 sounds good to me. Oh, yeah, okay. 3. 3413. Okay, cool. And then I think they're going to ask the same question. So it's probably here. If 100 fertilized were approximately how many of them? Well, 34% of those 100 would be 34 of them. And would it be unusual for an egg to hatch in less than 15 days? Why do you think it would be? Would it be? Probably. The reason is because, look, even back when we looked at 16, even hatching in less than 16 days is pretty unlikely. It has less than 2% chance. So if less than 15 is going to even have a lower probability. And the kind of threshold we use is 5%. So the probability of an egg hatching in less than 15 days, oh, they want the actual probability. Okay. So it's going to be a z-score of negative 3. So we can look that up on our table. -3. It's here, 0.0013. So that's pretty unlikely. So let's say 0.0013. So it would be unusual since the probability is less than 0.05. Okay? Cool. All right. What questions do you have? Any? All right. Cool. Sounds good. Anything else? Any other questions you'd like to ask before we get going? Yes, no. Okay, cool. Perfect. All right, so I'll bring your exam tomorrow and let you take it home. Did I just get rid of the wrong thing? I sure did. I don't think. No, don't say that. Oh, no, I didn't. Oh. Can we just, like, skip to December? Oh, fun stuff. I need that.
Are you keeping Chapter 8's homework due tomorrow night?
Chapter 8, no, I'll probably push it back to Monday. Okay. I'll leave Chapter 7 where it is, so finish that up this week. I'll push it back. Yes, finish up Chapter 7 by tomorrow, yeah. Just do tomorrow. I need that e-text back, that's why. All right. Now we can get back to work. For realsies. All right. That was user error. That was my fault. Okay. So where were we? We were talking about the idea of oh, I remember what happened. Yeah, so I lost those slides because my computer randomly shut off on me in the middle of one of my lectures in my next class. So I kind of left off. I lost those annotations. You can see them in the video. I just don't have the saved slides. So sorry about that. So I'm just going to have to pick up where we left off because if I recall correctly, where we left off is we were looking at we had this idea where the statistics we were interested in, I listed that off right. We were interested in maybe the mean, maybe the standard deviation, and then the last thing I was telling you about was, well, sometimes what we're actually interested in is proportions. Yeah? Okay. So we kind of like reviewed the notation for that. So you have the idea of the population versus a sample. And for the mean, we call that mu. For the sample, we call it x bar. Standard deviation, we call that sigma. Sample, we call that s. We call population proportions p, and then we estimate them with sample proportions. We call them p half. All right? So what I showed you yesterday was I looked at some data because we had, yesterday in class we had a situation where 25% of us worked full-time. That was the situation. And I showed you what would happen as we sampled people from a population who actually like worked 25% of the time. And after I took enough samples and calculated a sample proportion, what happened to that population proportion? Or I'm sorry, what happened to the sample proportions? What happened to the shape of their distribution? Yeah, it got more normal as I took more samples. And so, because you remember yesterday we looked at like a graph when I only had 5 samples, right? It was like something like our graph looked like this, right? And when I had when I went up to 30, what happened? They got closer together and it started to look a lot more normal, right? And then what happened when I did even more samples? Didn't I do even more than 30? I think I did more, yeah, like 80. And then what happened then? Yeah, everything was nice and, you know, it wasn't exactly normal. It looked something like this if I remember right. But it looked like that, right? And then the whole time, where was the center of this? It was right about 0.25. Right? The center of that distribution was right around 25%, which was the true population proportion, the way I simulated the data. I simulated it to be exactly 25%, or it was about 24.9%. Okay? So what we notice is that as you take more samples from your population, the sample proportion, not only is it centered around the truth, but it also has this nice normal distribution, which is exactly what I was hoping for, because that's promising because we know a lot about normal distributions, and we know how to calculate a lot of probabilities associated with normal distributions. All right. So it turns out this will always be the case. And just like the sample mean has these nice properties, there's the central limit theorem also applies for proportions. Okay. So, how do you phrase this? So, for a population, with a true proportion P, for a large enough sample size, so this is kind of like last time, it relies on taking in a big enough sample. Then the sample proportion P hat will have an approximately normal distribution. Okay, and the mean of the sample proportion is going to be centered around the true proportion, just like we saw with the sample mean. So the sample mean was centered around the true mean. The sample proportion will be centered around the true proportion. And the standard deviation of that statistic is going to be this. All right. So that's the square root of p times 1 minus p over n. Okay. And so notice we're dealing with proportions here, not percentages. So it's written in the decimal form when we're talking about this stuff, not the percentage form, the decimal form of those. All right. So this is pretty cool because it means that even if we're interested in proportions, we can still take advantage of the normal distribution, and we can still calculate, say, like probabilities with the normal distribution or percentiles, things like that. Yeah. Now, what's the caveat here, or the kind of the sort of vague thing in this definition? Yeah. This is the problem. Okay. This is really the problem that we have. So what happens is that depending on what your population proportion is, it can actually change the skewness of your distribution. So like I'll show you an example here. I'll just produce some data real quick and I'll show it to you. Maybe. Oh well, it's better than shutting down. So I'm going to do, this is what we didn't actually really do this, but I'm going to simulate some data from, we're going to say a binomial distribution. And so let's see, I want to go, say I want to do it like 100 times, and maybe first column. Let's say that this doesn't matter. So I'll do one where you're doing like a 50-50 split, okay? So like the things are equally likely. Okay. So wait, I want like, say, not 100 trials. I want maybe 10 trials. So say you're gonna like flip. This is like you're flipping a coin 10 times, right? A fair coin 10 times. And if I go ahead and do that, and then what it does is it measures how many like successes you had, like number of heads. So if you look at the histogram of those flips, well, what does it look like the shape is? It's already pretty normal. So if you're looking at if your sample proportion is a 50-50 split, then you're already going to be looking at a pretty normal distribution in your results, right? The problem is that if I do something that's not a 50-50 split, so again, say I'll do this 100 times in one column, and let's say 10 trials, but let's say that it's something that's not equally likely to succeed. So you're looking at something that only has maybe like a 0.25 chance of success, like a 1 in 4 chance, like our example with people working. So now I'm sampling 10 students, and there's a 25% chance they work full time. Well, if we look at that histogram, okay, here's binomial. They're both called binomial 1, but whatever. Not that important. We'll stack them on top. Right? Then what do you see? What happens to it? It has more of a skewed shape, right? Yeah? I think it's because we use the same x-axis. Maybe I don't want to do that. If I just do this, what happens? Does it still do that? Oh, yeah, it still does. But you can see it has more of a skew shape. And it gets even more extreme if your probability of success gets really small. So let's say that I only have like a 5% chance of success, right? Say that was my scenario. And I look at the histogram of that last one. Then that's going to be really skewed, right? I mean, that's like, this is about as skewed as it gets, where everything's piled up at the bottom and it trails off really fast. So it actually, it's not just a function of your sample size. It's also a function of how likely or what the true proportion is. So the general rule of thumb that we use, I'll put it over here. What we try to check is what we want to see n times p times 1 minus p. We want to see that to be at least 10. That's the rule of thumb. And again, this is just, that's all it is. It's a rule of thumb. Just like we arbitrarily said, if you take 30 samples, then the sample mean is about normal. That was sort of an arbitrary number that we picked by just looking at a whole lot of data sets. And we said typically, as long as you take 30 samples, you're safe. Well, with proportions, typically, as long as your sample size times the proportion times 1 minus the proportion is more than 10, then you're pretty safe. Okay. So what you can notice then is what's going to happen, though, is that if your p is really small, right, that's going to mean that your n is going to have to be bigger, and vice versa. So if your p is really big, then this will be really small, and your n will have to get a lot bigger. All right? Okay. So I'll show you an example here. All right, so this was an example they showed in the book. So they took a survey, and the survey showed that 39% of Americans believe that marriage is obsolete. Seems like a high number, considering what percent of people actually ultimately end up getting married. But apparently 39% of people believe in marriage, whatever they're calling marriage, as it is obsolete. That's what they say. All right, so let's say that's true, and 39% of Americans really do believe marriage is obsolete. What I want to know is, let's say that you go out and you sample, let's say 500 Americans. What I want to know is what's going to be the sampling distribution of the sample proportion. So p hat, which will be the proportion of the 500 who believe this. Okay? So what's going to be the sampling distribution of that? So assuming that 39% really do believe this, and you go out and you talk to 500 people, so you randomly select them, then what's going to be, how will that sample proportion be distributed? So ideally, we're going to try to use the central limit theorem. Now, before we use that, though, we need to do a sample size check, basically, right? So the first thing we do is we check our sample size. Is 500 enough? Okay, so what we check is n times p times 1 minus p. So we're talking about getting 500 people. We believe apparently 39% think it's obsolete, and then which means 1 minus that would be 61%. right? If 39%, then 1 minus that's 61%. What does that come out to be? 500 times 0.39 times 0.61. Somebody want to do that for me real quick? I can pull mine out and try that as well. But
I got 118.95.
okay, 119.95. 118 point whatever something. Okay, either way, it's big enough. 118 point something something. So it's definitely bigger than or equal to 10. So we say, okay, so the sample size checks out. That's good. All right. So then that tells us if the sample size is big enough, then the central limit theorem applies to this. Okay. So as long as our sample size is big enough, then the central limit theorem applies. And if the central limit theorem applies, it tells us then that p hat is going to be approximate. No, you didn't. Come back. Come back. Yes. Making me nervous. It's going to be approximately normal with its sample mean. It should be centered around the true proportion, which is 0.39, right? And its standard deviation is going to be the square root of p times 1 minus p over n, which is the square root of 0.39 times 0.61 all over 500. Okay, so we got to do 0.39 times 0.61, divide that by 500, and then we need to see, then take the square root of that and see what that comes out to be. All right.
So I got 0.
What's that? 61%? Because that's 1 minus 39%.
Oh.
Yeah. Or 100 minus 39%, but it says a proportion. Right. So it's the complement. And what do we get? Someone said it.
I got 0.02. How many decimals are there?
Let's do 3 decimals. Why not?
0.022.
0.022. Let's do 4 decimals.
Okay, 0.0218.
0.0218. Anybody else for that? Okay. So you got to do this stuff and then take the square root of it all at the end. Okay. Yeah, that looks about right. So it's saying that if you think about this, it's going to be centered around 39%, but it's going to have some standard. It's going to have some deviation, right? Sometimes you'll get a little higher proportion. Sometimes you'll get a little bit lower proportion just based on your sample, and the standard deviation of that is going to be about 2%, right? So this is basically centered at 39% with a standard deviation of like 2%. That's more or less what it's saying here. Okay. Now, so one thing you might ask is you say, okay, well then let's say you did do that. So if you did randomly select 500 people, then what would be the probability that your sample proportion was, say, between, I don't know, 40% and 45%? Right? What's the probability that just by random chance you end up with a sample that gives you a higher proportion, 40 to 45%? All right? So, how would we solve a problem like this? Z-scores. Yeah. That's right. So, we're going to do just like we did before, but now we're going to use this mean and this standard deviation. Okay, so we're looking from, so if we're looking, we know that, so we're looking for probability, sample proportion between 40 and 45, right? So it's a distribution that's centered at 39, so maybe here's 40, here's 0.45. Yeah, we need z-scores, okay? So we're going to get 2 z-scores. We need to get a z-score for 0.40. So you're going to do that minus the mean divided by the standard deviation was 0.0218. That'll be the z-score for 40%. And then you need to go get a z-score for 45%. So it's going to be 45% minus 39% over 2.18%. Okay. And what do you get for those z-scores if you round those to 2 decimal places?
For the top one, I got 0.46.
0.46? Sounds reasonable. 0.46, anybody get that? Yes? No? Maybe so?
Bottom
Okay.
one, I got 2.75.
2.75 upstairs? Or for the bigger one? Maybe? Sounds about right to me. Does anybody able to confirm that though? 2 point. Okay. 2.75. Right. So what we're really going to do is we're going to go get this probability off the z table between 0.46 and 2.75. And how do you do that? Well, we need to do what? We need to get the big probability, right, and subtract off the small probability. So we just need to go look these up in the table. So let me get out of here. So let's go to I'll look up 2.75 first. All right, it's back. Okay. So 2.75 is going to be positive. So you go to my positive side. So scroll down. That's going to be 2.70, 1, 2, 3, 4, 5. So that's 0.9970. So 0.9970 minus, now we got to go look up 0.46 in our table. So 0.4, 0, 1, 2, 3, 4, 5, 6. And that's 0.6772. 0.6772. All right. And now we just do the subtraction. And what's that come out to be? 0.3108. I should stop guessing. Is that it? No? 3198. 3198. Yeah, that sounds reasonable. All right. So there's about a 32% chance that you're going to end up with a sample proportion somewhere in that area. And that's just by random chance, right? So does that seem pretty likely? Does that seem like something that could definitely happen? Sure. And so what it's showing that is that even though the truth is 39%, and even though the sample proportion should be pretty unbiased, it's going to be right around the truth, sometimes you're just going to end up with big sample proportions just by random chance. You're just going to end up with a group of people who happen to be more likely to say marriage is obsolete. Just like sometimes you're going to end up with groups with smaller percentages. It just happens. Okay? All right. The trick is, and this is just like the mean, the trick is now recognizing that we're taking multiple samples and we're interested in proportion, we have to do that upfront work of getting that sample standard deviation, just like with the means. All right? But if you know the formula, it's not too bad. All right. So let's say that, let's look at another application here. Okay. So according to a survey, 10% of Americans in, say, 2002 were afraid to fly. So, like, they won't get on an airplane. All right? Does that sound about right? You think 10% of people are afraid to fly? Sounds about right, maybe. I don't know. Okay? Should you be afraid to fly? Yes or no?
No.
Some people say yes. Why? Because it's unnatural. We're hurtling ourselves through the air at 600 miles an hour, and it's just wrong, right? But should you actually be afraid to fly? Statistically?
No.
Why not?
Because you're more likely to die on your way to work.
You're way more likely to die on your way to work than you are to get. Yeah, can you even remember the last time we had an airliner crash in the United States?
Yeah.
Can you remember? When was the last time a commercial airliner crashed in the United States? September 11th. There was one. There was one since then. There was that one that landed in the Hudson, but nobody actually was killed. They all survived. Yeah. No, seriously, commercial airliners are actually really amazing if you think about it. Think about how many millions of people fly every single day. Like every single day, they're taking giant metal tubes and launching them across the country with millions of people. And when was the last time anybody got injured on one? I mean, they're really incredible. Anyways, yes, that's true. You should not be, statistically, you are way more likely to die in your car than you are in an airplane. Way, way more likely, right? In fact, really, it's pretty interesting because I have kids, and I constantly see these things from like other mothers that my wife knows, and they're all like really paranoid about this stuff. You know, all these things that can hurt your kid, and all these like things you need to do safe about your kid. But my point always is that the single most dangerous thing you can do with your child is to put them in a car and drive down the freeway. That statistically, that is the most dangerous thing you can do with your kid, and yet we do it all the time, right? But they won't let their kid like play outside in the front yard by themselves, right? But that's just the statistician in me. But anyways, flying is pretty much like one of the safest things you can do in the world, besides like stand still in your bedroom for 5 minutes or something. Like there's not many things that are much safer than getting on an airplane and flying. So anyways, you shouldn't be afraid to fly, but that doesn't mean you're not. I understand that. People have irrational fears, and that's okay. Okay? All right. So anyways, you never know. It's true. You never know.
As long as you make it past takeoff and landing, you're fine. The rest of the part's safe.
That's right. Right, that's the problem. People have problems when they have no control over it. You feel like you have control over your driving. Yeah, it really has to come down to that thing. So, regardless, 10% of people were afraid to fly in 2002. Okay, so let's say that you took a survey today. So you go out and a survey this year of, let's say, 1,100 people. It showed that 121 were afraid to fly. Okay, 121 of those 1,100 people surveyed said, "No way, I'm not getting in that thing. I prefer staying on the ground." Okay, and so my question is, does this indicate, say, that sort of the fears have changed? Like, is this a situation where it looks like maybe more or less people are afraid to fly than they used to be? Okay, that's what I want to know. And the way we're going to do this is essentially what I'm going to see is, first off, what was my sample proportion for my particular sample? What percent of my people were afraid to fly? So, no, in my sample. So this is like saying this is what was true in 2010, and that's the truth. That would be like a sample proportion. But what would our sample proportion be? Yeah, so you go and you say 121 out of 1,100. Okay, and it's 0.11. Is that it? That's it? It's exactly? Oh, nice. 11 times 11. Oh, yeah, okay, 121. Cool. Yeah, so it's exactly 11%. Now, the question is, I talked to a lot of people, right? So I talked to like 1,100 people. That's a good sample size. And in my sample, 11%. Does that actually mean now that more people are afraid to fly than it used to be? Okay. Well, what's one way we could gauge whether or not it seems reasonable? It kind of has to go back to sort of like the drive-through example we did yesterday. What's one way we could gauge that? So one way we could say is is 11%, say, unexpected or unusual if the truth is 10%? right? That's one thing we could ask. Say, okay, what if the truth really still is 10%? Then how likely would we actually be to get a sample with 11% being afraid? Okay. So that's what we're going to answer. Now, of course, what we need to do here then, essentially we need to answer the question, what's the probability that p hat is more than 11%? Because if it were true, right, if 10% is really the truth, our sample proportion should be centered around 10%. But sometimes we're going to get higher proportions, sometimes we're going to get lower proportions. You know, we saw a sample proportion of 11%. I want to know, what's the likelihood of that happening? Something like that, or more extreme. All right. Of course, what do we need to know here? I know where the center should be. What do I not know? Standard deviation, yeah. Do you think the sample size here is big enough? Probably. It's pretty huge, but we should probably check just in case. So first, I'll check n times p times 1 minus p. So that would be 1100 times p was 10% times 1 minus p would then be 90%. And that comes out to be, what? A lot, I feel like. Still a pretty big number. 99 sounds reasonable. Okay. So 99, yeah, that's plenty big, definitely bigger than 10. So we're okay there. So then then the central limit theorem is okay. So then we know that it'll be normally distributed. It'll have a mean centered around the true proportion, which we're assuming is 10%. We're assuming it hasn't changed. We're going to see if this seems like unusual. And then we're going to calculate the standard deviation, p times 1 minus p over n under square root. So it's going to be 10% times 1 minus that would be 90%, all divided by 1100, which would be what? Somebody do that for me and see what you get, because I have no idea what it's going to come out to be. 0.0090. 0.0090. Anybody else get that? Takers? I know it's 0.0 something, so I'll write that down. Anybody get something different? Your calculator got angry when you did that? Too many numbers. You gotta put in parentheses for the square root, I think. Well, it depends what kind of calculator I have, but yeah. Did anybody get any numbers? That I got a 0.4. I got a 0.7. Someone say 0.7? This is getting pretty. All right. He's gonna make me do it. What was it? What are we getting?
00904.
But you only want 4
Okay.
right?
Yes.
So it's 0090.
Yeah, we'll say 009. And 0. Yeah, if we rounded it. So we don't need to include that. Yeah. We could put the 0 there, but that would be redundant. So there you go. All right. So then if we actually sampled 1,100 people from a population that really was 10% afraid to fly, that sample proportion, it should be centered around 10%, but it's going to have some variance, right? Sometimes it'll be a little higher, sometimes it'll be a little lower. And the way it's going to vary is it's going to have a standard deviation of 0.009, so just a little less than 1%. That's the idea. All right. So now the question becomes, what is this probability? What's the probability that we would see a sample of 11% or more? Okay, well, how do we get that answer? Z-score? Sure. So we'll just go down. I'll bring it over. What we're looking for here is, centered around 10%. Here's 11%. I want to know this probability. My mean is 10%. My standard deviation was 0.009. So we just need to do what? Get a z-score for 11%. So I saw an observation of 11%. I'm assuming the mean, I'm going to see what happens assuming the mean didn't change. It's really 10%, which would mean the standard deviation would be 0.009. And what does your z-score come out to be there? 1 something? Something a little over 1? 1.11? Yeah, that sounds reasonable. All right. So then what I'm really looking for here is on the z-table, I just need to go to the z-table, Here's 1.11. I'm looking for that. All right. So that would be 1.1. So I'll go to the positive side this time since I'm already there. 1.11, that's 0.8665. But that would be down here, right? That would be 0.8665 from the table, which means the top would be what?
0.1335.
Yeah. So that's your. All right. So then the question becomes, does 11% seem unusual if the truth is 10%? Does it seem unusual according to what we're looking at here? Not really. You know, it's saying, remember, we kind of use an arbitrary cutoff of 5%. Things that happen less than 5% of the time we consider unusual. And in this case, even just by random chance, we're going to see percentages of 11% or more, like 13% of the time anyways, just by random chance. And that's pretty likely. That's not really enough for us to really be concerned. Right? Yeah. So, what questions do you have about that? All right. I mean, so at the root of it, it all comes down to basically calculating z-scores and going to the z-table. It's just that when we're doing sampling, we have a step we have to do first, which is getting that sample mean and sample standard deviation. So you need to be you just have to be careful. So here I'll just kind of summarize it for you here, right? So the idea is there's basically a couple possibilities, right? So if we're just looking at one observation, right, you're just randomly selecting one observation out of this thing, then your z-score, what you're going to do is you're just going to use the z-score as we first learned it, right? Observation minus the population mean divided by the population standard deviation. That's what you use. Now, what happens though is that if you take n samples and you calculate a sample mean, right, then the z-score you're going to use, it's going to be your sample mean minus the true mean, and your new sample standard deviation is going to be that sigma over root n. That's going to be your z-score. So you have to ask yourself, am I picking up one person or am I picking up a lot of people and averaging them? Or the third scenario is that you take n samples and you're not interested in a sample mean, you're interested in a sample proportion, right? And if that's the case, then your z-score is going to be your sample proportion minus the true proportion, which is your mean, divided by the square root. Your standard deviation on here is p times 1 minus p over n in the square root. Okay? And this was what we talked about in chapter 7, right? Just taking like one thing from a normal distribution, and this stuff over here is the stuff that comes out of chapter 8. When you're sampling multiple people and you're calculating a statistic like a mean or a proportion. All right? But the process is the same. You're still going to take that z-score to the z-table, and that's how you're going to calculate probabilities associated with these random variables. Okay? Feel semi-comfortable with that? What questions do you have? All right, so focus on getting chapter 7 done right now. I'll pass out an exam tomorrow, and then you can work on the exam or chapter 8 homework over the weekend. I'll keep the chapter 8 homework open until Monday. Guess you'll work on that. Okay? What's up?
So I just, like, a lot of them you can see that I showed, like,
Okay.
how I got that, so. Is that okay? Or do you want it on a
That'll be
separate
okay.
sheet? Okay.
I got a question.
What's up?
So I was looking at my grade yesterday, and my activity 3 shows a 0.
Okay.
I submitted it online. I was wondering if maybe it didn't go through, or
It may be. The best bet is, can you just, so on, let me save this before I get it.
I thought I put it
yeah, let me see.
I thought I put it where it said document 3 submission.
Yeah, that's where I would want it.
That's where I thought I put it, but if it's 0, clearly it didn't go through. I still have it on my computer, so I can resubmit it.
Yeah, just put it in there again, and then you email me when you do.
Okay. Thank you.
Sure. What's up?
I won't be able to be in class tomorrow,
Okay.
so I was wondering if I could pick up the exam.
I'll post a copy of it in my stat lab
Okay,
once tonight.
okay,
So you can just download it and print it off
okay.
yourself.
All right, thank you.
Here's mine.
Perfect.
Exam 2.
Thank you.
Uh-huh.